David Spears, civil engineering instructor at Texas Tech University, talking about statics, CE 2301. This is a fluid pressure problem, and what we have here is a tank that's 3 feet wide coming out of the page, and these are the dimensions of it. And I have the sloping surface A to B that I'm going to focus on in the problem. The fluid has a specific gravity of 40 pounds per cubic foot. And these are the dimensions. Okay, I've got to start off with the fact that the pressure P due to any fluid is the gamma, the specific gravity, times the depth. So if I just look at it over here, I've kind of blown up this part of the tank, show a little bit bigger scale. At the point A, that's 2 feet down from the top, and the tank is assumed to be full, the pressure 2 feet deep is just 2 times 40, or 80 psf. Similarly, at a point B that's 4 feet total down from the surface, the top, the pressure is just pressure 4 times the specific density, specific gravity, 40 pounds per cubic foot, 160 psf. Okay, so those are two important numbers that I need to continue on with. Now, the key thing to this kind of problem is, the interesting thing about fluid pressure is it's exerted normal to whatever surface solid surface that it's up against. And so even though this sloping surface is like this, there's still going to be a even upward fluid pressure exerted on that surface perpendicular to it, and the magnitude of that pressure is at whatever depth it is below the surface. So that's, I've already figured those numbers, is 80 psf at A and 160 psf at B. So there's my pressure distribution representation. I can compute this distance here from A to B on the slope, knowing that it's 1.5 horizontal, 2 feet vertical. I recognize that as a 3, 4, 5 triangle, so that makes it 2.5. If I don't recognize it, I just get the square root of the sum of the squares, and that's 2.5 feet in length. Now I'm going to take that whole pressure distribution block, and I'm going to rotate it so I can look at it kind of just as a beam. So this is point B now. I've taken the whole thing and rotated it 135 degrees or something like that. So I have 160 psf on this side and 80 psf on the A side. I've got my 2.5 like a span of a beam. So now it's just find the resultants of that pressure, load, and where it occurs, where the total resultant occurs. So I break it up into a triangle and a rectangle, just like this with my dashed line there. This triangle has a height of 80, which is 160 minus 80. Its length is 2.5 feet, and its centroid is 2/3 from its tip of the triangle, 1.66 repeating feet from the right. So my resultant force, FR1, is 1/2, it's just the area of that triangle, 1/2 80 times 2.5 feet is the base. So it's 100 pounds per foot. I've got to remember I'm working in pounds per foot of width. Eventually I'm going to have to multiply by this 3 foot width to get a resultant force in pounds. Similarly, the area of that rectangle is FR2, the resultant force number 2. That is the height of the rectangle, which is 80 times its width, 2.5 feet. I get 200 pounds per foot. So my resultant is just the sum of those two numbers. 100 plus 200, or 300 pounds per foot, times my 3-foot width of the tank is equal to 900 pounds. And over here I'll figure out where it's applied. I've kind of redrawn my pressure distribution diagram over here. I have FR1 of 100 pounds acting at 1.67 feet. I've simplified it to. FR2 is 200 pounds per foot acting in the middle of that 2.5 foot span, or 1.25 feet. So just like I figured my centroids and my resultants for the last 2 months in this class, I just really kind of want to sum moments about point A, which is going to be the force times the distance, and which is going to be the summation of the forces times the distance. I add them up. The summation of FDs is 100 pounds times 1.67 feet from A, plus 200 pounds times 1.25 feet from A. It's 416.6 repeating foot-pounds per foot. I've written it that kind of strange way because I've still got I've got pounds per foot times that distance of feet. So my D distance, remember that D is the sum of the forces times their distances divided by the sum of the forces. Remember we figured M is equal to, or D distance when we're working on centroids is equal to M divided by F. So that's 416.6 divided by my resultant force, and I'm consistent because I'm just working in pounds per foot of width. 416.6 divided by 300, this number over here, is 1.39 feet. The 3-foot would divide out if I put that all in there. If I wanted to know the reaction at point B, say for a fastener or a weld, if I was welding that part of the tank, how much force would I have to resist? Once again, I'm just summing. It's just like a beam reaction. I'm summing moments about point A. BY, the distance is 2.5 feet, minus this number up here, which is sum of FDs, 100 times 1.67, 200 times 1.25. That's this number 416.6 divided by 2.5. Then I want a force and not just a force per foot. That makes that reaction at B over the whole width of the tank 500 pounds. Sum of forces, I can figure out what the reaction at A is. 900, the total resultant force, minus 500, my reaction at B, makes it 400 pounds at A.